The building sector accounts for more than 40% of the global energy use and 30% of greenhouse gas emissions. Population growth, rapid urbanization, and the increase in the ownership of personal appliances are some of the main leading factors that are increasing the energy consumption and greenhouse gas emissions. With renewable energy technologies becoming cheaper every year, the future of the electrical grid will depend on our ability to align high peaks of electricity consumption with peaks of renewable energy generation. Renewable energy technologies have an extremely low variable cost, which makes them very competitive in the day-ahead and real-time electricity markets, which helps reduce the price of electricity. However, even if we perfectly aligned renewable energy generation and energy demand, we still need to transmit all that power very long distances, which requires significant investments in the power transmission and distribution infrastructure, and can cause constraints in the power lines. This phenomenon is particularly noticeable in hot and humid climates, where demand for air conditioning in the summer makes electricity prices skyrocket and cause dangerous energy blackouts, like it has happened in the state of California in recent years. So, how much energy we consume is just as important as when and where we consume and generate that energy. Distributed energy generation can help decrease the amount of energy that needs to be transmitted to residential areas, reducing the constraints in transmission power lines, lowering the prices of electricity, and reducing the need for additional investments in the power transmission infrastructure. Despite all these advantages, some distributed energy resources, such as solar energy, can be a source of other problems. Abundant photovoltaic generation during the day reshapes the load profile of many communities by creating multiple peaks and valleys of energy use, which are known as the duck curve. The duck curve puts a stress on the power grid by forcing generators to ramp up energy generation very rapidly. This increases the price of electricity and CO2 emissions, as many of the power plants that can ramp up generation very quickly do so by burning natural gas. A possible solution to this problem is to store energy over generation at the distribution level and release it during the peaks of high demand. The increasing adoption of electric vehicles and other storage devices offers us an important opportunity to better control the demand for electricity. By charging these devices at the right times, and even releasing part of the stored energy back into the power grid, we can flatten the duck curve. There are many different ways in which we can control these energy systems. The traditional approach would be using a rule-based controller, in which the control system will take one or another decision or control action based on different conditions and whether or not they are met. Other control approaches that are more advanced are the model predictive controller, which will build a model of the system that is going to be controlled, and then is going to run an optimization problem in order to find a close to optimal control policy. The problem with this type of controller is that it's only as good as the model of the system, and therefore if the system that is under control is changing over time, for example, if we have a neighborhood with many different houses or buildings, and then we start integrating photovoltaic panels or electric vehicles, then this controller would need to be redesigned, and it would no longer work because it's not adaptive. And also it's more expensive because it needs an engineer that starts developing all these models and tuning the controller. And that's why we focus on a different type of controller, which is known as reinforcement learning. That is a model-free type of controller, so it doesn't require to build any models of the systems that are going to be controlled. And it's also adaptive, which means that if the systems change over time, the controller adapts and continues to find new optimal policies. And it does this by taking different actions under different states or conditions, and then observing what's the response of the system that is controlling or the environment. And by taking actions under different states and observing the different rewards that is obtaining, it is able to maximize the long-term sum of rewards which is an objective function. And that's why this type of controller has become very popular in recent years. And we've seen an explosion of research being done in this topic for urban energy systems, for electric vehicles, domestic appliances. There's a lot of research that is being focusing right now on using reinforcement learning to control these energy systems because of its adaptiveness, its cost effectiveness, and then also because it can leverage the power of historical data in order to find close to optimal solutions. In previous research, we created CityLearn, an OpenAI gym environment for the implementation of reinforcement learning for urban energy management and demand response. Now, we use the CityLearn environment to implement our own multi-agent reinforcement learning controller in a simulated scenario of 4 different neighborhoods and in different climate zones and different building types. We used Energy Plus prototype buildings to create the different microgrids and use reinforcement learning to coordinate the energy they store in chill and domestic hot water tanks, with the objective of flattening the overall curve of electricity consumption. Each building had its own reinforcement learning controller that decides the amount of energy that is stored or released by the energy storage devices. At the same time, the storage devices receive thermal energy from heat pumps and electric heaters. To measure the performance of the algorithm, we analyzed 5 different load shaping metrics for a full year. To design our load shaping controller, first we had to design the reward function that represents the objective of the controller. In this case, the reward function of each reinforcement learning agent is the net electricity consumption of every building raised to the power of different coefficients. We observe that the higher the exponent coefficient is, the better the performance of the algorithm, up to an optimal coefficient of 3. This type of reward is a single agent reward, since it only depends on the electricity consumption of the building itself and not the electricity consumed by the other buildings. To improve the performance of the reward function, we added a collective component to it. We multiplied the square value of the electricity consumption of each building by the net electricity consumption of the entire district. The objective of each agent was both to perform load shaping on its own building and at the district level. After training the controllers for 10 epochs of 1 year, we observed that adding this collective component didn't improve the performance with respect to the single agent reward. The reason behind this is that each reinforcement learning agent didn't have state information about the other buildings in the district. We corrected this by allowing the agents to share predictions of the electricity consumption of their respective buildings with each other, and that's why we developed MARLISA, a multi-agent reinforcement learning algorithm with iterative sequential action selection. MARLISA is built upon the soft actor critic algorithm, a state-of-the-art model-free off-policy reinforcement learning algorithm that can learn from historical data and control systems that have continuous states and actions. In our MARLISA control framework, each building agent collects data and trains a regression model that predicts its own electricity consumption as a function of some states and the possible actions that the soft actor critic controller can take. Then, MARLISA creates a randomly sorted line of building agents that will select their actions sequentially. The first building in this line selects an action using SAC, predicts what its electricity consumption will be if such action was taken, and shares this prediction with the next building in the line, which uses this prediction as a state variable. This next building then selects an action and predicts its own electricity consumption, which is added to the prediction of the previous building and shared with the next building in the line, and so on. When the last building in the line selects its action and makes a prediction, the information is shared with the first building in the line, and the process is repeated again iteratively until every building has an estimation of the net electricity consumption of the rest of the district in the following time step. In addition to this prediction variable, buildings also share another variable that represents how far they are in the decision-making line. This whole process happens within the same time step of the simulation, and once MARLISA runs the last iteration and every agent has selected an action, all those actions are taken and the simulation moves to the next time step. Sharing the aggregate predicted electricity consumption ensures that no building in the grid knows how much energy any other building is going to consume. The algorithm is also scalable, as the number of shared variables between any two buildings is always constant and does not increase with the number of buildings. When we combine the multi-agent reward with the MARLISA control algorithm, the controllers learn faster and better, improving their performance across the 4 different climate zones where we tested them. The final average daily load profiles show how the algorithm successfully flattened the duck curve by properly coordinating the energy storage in the different buildings. These results we've shown so far were obtained by training the algorithm across many epochs using the same simulated data, which is not something we can do in real-life situations. That's why we also evaluated the performance of our controller in a 5-year case study in the same type of district. In order to learn, reinforcement learning needs to take exploratory actions at first and improve its performance over time. Therefore, it is critical to analyze how long it takes until the algorithm starts to perform well. Our results show how MARLISA was able to outperform our baseline rule-based controller after only a year of training. And we were able to improve the performance during the exploration phase by using the rule-based controller itself to perform the exploration instead of doing random exploration. This slightly decreased the long-term performance of the controller, but greatly improved the short-term performance. In conclusion, it's becoming increasingly important to control the energy that we store and consume, and the adoption of electric vehicles and other type of storage devices is only going to accelerate this trend. In this paper, we have focused on introducing a reinforcement learning controller called MARLISA, which focuses on coordinating different residential agents and how we can store energy in a way that we flatten the overall curve of electricity consumption. Reinforcement learning, as we mentioned, has many advantages because of its adaptability, its ability to learn from historical data, and also because it's model-free, which makes it much more cost-effective for its implementation in residential areas. We implemented our reinforcement learning algorithm into CityLearn, which is a reinforcement learning OpenAI gym environment that we have developed for the implementation of reinforcement learning for urban energy management. If you want to know more or get started with CityLearn or reinforcement learning, please visit our website, citylearn.net.